Mark Meerschaert is the author of a very successful textbook on mathematical modeling. He's a professor of statistics at Michigan State University, and I'll begin with a quote about mathematical modeling from his book. He says, "Mathematical modeling is the link between mathematics and the rest of the world. You ask a question, you think a bit, and then you refine the question, phrasing it in precise mathematical terms. Once the question becomes a mathematics question, you use mathematics to find an answer. Then, finally, and this is the part that too many people forget, you have to reverse the process, translating the mathematical solution back into a comprehensible, no-nonsense answer to the original question. Some people are fluent in English, and some people are fluent in calculus. We have plenty of each, and we need more people who are fluent in both languages and are willing and able to translate. These are the people who will be influential in solving the problems of the future." I think we alluded that a little bit in the last example involving the company that was pricing the new product, right? There are a lot of stages to solving the problem that don't just mean turning it into math and getting an answer that comes out. You actually have to do effort to think of what the decision variables are, what is under your control, what's your objective, and so on and so forth. And that's one of the skills you're going to develop throughout this course. If you learn nothing else, it's I hope you gain some insight into how you can use math to attack problems that occur in your everyday life. Underfitting and overfitting is typically a phenomenon that you see mentioned in statistics, although I think it's appropriate to talk about generally in modeling something. If you look at these dots I've drawn here, right, most of us would look at these dots and say, okay, what's going on here? You're going up and then you're going down, right? Globally speaking, that's the trend there. When you're building a mathematical model, it's important to make sure you have enough variables to capture all of the important features, but you don't want to have too many to overly complicate the model and introduce kind of spurious phenomena that aren't really there. I would call the first problem underfitting, right? This is me trying to fit a line to these points. And you'd say, well, that it isn't a line, right? The curve is more complicated than that. So I didn't give myself enough variables to approximate that curve correctly and to model my problem faithfully. Overfitting would be if I've given myself some crazy a lot of different variables that I can optimize and enabled myself to way too much freedom. And you'd say, okay, here's the curve, and it sort of perfectly fits everything that you see there, but it's not very helpful. It doesn't actually tell you about trends or anything. I wouldn't trust this curve for extrapolating anything in the future. It doesn't capture any of the global behavior that we identified up there. And so I'd say this one in the lower right is just right in the sense that it captures the behavior the way we want it to. Maybe I'm wrong about that, right? I'm saying it's just right. Maybe it isn't actually the case. We'll never know for sure. Mathematical modeling is not an exact science. But it's important to keep these sort of features into account when you model things. Try to reduce the number of variables and parameters just to the point that you're still capturing the model faithfully. And having said that, let's get technical. I'm going to introduce you to what's called a linear program, which is something you're going to learn a lot about over the next few weeks. A linear program is a mathematical optimization problem. You don't even know what that means yet. It's completely fine. In which the objective function and all constraint functions are linear. Okay, so you look at this picture here, or look at this chart. I've written the word maximize. Okay, that means that I'm trying to maximize something. It means I'm trying to make as much money as I can, maximize my profit, or maximize the crop yield, or something like that. I've got to maximize there, and then my personal convention is I always like to write the variables right under that word. Not everyone does that. I even violate it myself later on in the slides. But I like it. It's good practice because you're telling the viewer, the user, whoever it is, you're telling them explicitly what the variables are. You're not telling them what they represent, but you're at least identifying them there. So you say maximize, and then I've got this thing at the top. This is called my objective function. I'm saying I am going to choose x1, x2, and x3. These are variables under my selection. And I want this thing here to be as big as possible. Okay, I want 30x1 plus 20x2 minus x3 to be as large as I could possibly make it. Okay, and now I have the letters ST. You see this a lot in optimization. Every optimizer knows that those stand for subject to or such that. And that means that everything below this ST, which is all this stuff down there, those are constraints. These are conditions that have to be satisfied. This ST is actually kind of redundant because once I've told you what the objective is, anything I'm writing below this is going to have to be a constraint anyway. But we would like to write that just to make sure it's clear that we're explicitly identifying that these are conditions that have to be met. So you'd maximize these variables, or sorry, this linear function of these variables subject to the following conditions. So we've got here 8x1 plus 4x2 is less than or equal to 640. 4x1 plus 6x2 plus x3 is equal to 540, and so on and so forth. Now, the reason I call this a linear program is because all of these functions are linear. There was no x squared, there was no sine of x, there was no e to the x, there was nothing like that. The most important feature of this model here, of this thing I've written down, is that everything is linear. I've allowed myself to have constraints with inequalities. I've got a less than sign here, I've got a greater than sign here, and I've got an equal sign there. Those are all fine, but all of these functions here have to be linear in my constraints, and my objective function has to be linear as well. That's why it's called a linear program. The most general form for a linear program looks like this thing here. So you have either a maximize or a minimize. You could have a minimization problem too. I could be saying minimize my costs. I could be saying make the smallest car that smallest cargo space that still obeys certain constraints, or whatever you like. Minimization objectives are completely common as well. And then you have some linear function of the variables as your objective, and then you have some less than constraints here, you have some greater than constraints here, and you have some equal signs here. Common question I get at this point, which is a good topic for discussion, is are you ever allowed to have strict inequalities? Am I allowed to say that this linear function is strictly less than b1? As opposed to less than or equal? The answer is no. That isn't going to be part of a linear program. By definition, linear programs allow you to have, they require that you have non-strict inequalities. You're allowed to have inequalities, but they have to be less than or equal to or greater than or equal to. The one sentence answer to that is because if you allowed yourself strict inequalities, you generally wouldn't be able to find a solution to the problem. And that's a good topic for discussion that we could certainly have. If you like linear algebra, then not a lot of people do, but if you do, I do, you would write it like this, right? You just use matrix multiplication and make all those constraints smaller, like that. So linear algebra, it makes a lot of this stuff a lot easier to write. The most famous example of a linear program is the diet problem. I'm going to skip ahead to this slide here because I like the fact that it has numbers on it. So the diet problem looks like this. What I've written here, you can ignore this linear program there. In fact, I want you not to look at it because I don't want you to think about anything that's going on. I've even written the solution, which we're going to kill as well, like that. Look at this table here. What I have written is the nutrition information for a bunch of different kinds of foods here. And I've written the price per unit of the food up there. And then here I've written down how many grams of that nutrient we have to consume in a day. Okay, so this says, for example, for protein, let's say a person needs at least 46 grams of protein. We're going to use lower bounds. We'll say you need at least 46 grams of protein, at least 65 grams of fat, at least 250 grams of carbohydrates. We'll say you have to have at least this much. And we'd say, okay, how about a slice of bread? A slice of bread costs evidently $2, which that sounds like some very fancy bread. But a slice of bread costs $2, and it has 4 grams of protein, 1 gram of fat, and 15 grams of carbohydrates. And then a jug of milk has 8 grams of protein, probably a cup of milk, that makes more sense, 5 grams of fat, and 11.7 grams of carbohydrates, and so on and so forth. So that's what this table here represents. So what's the point of this table? So I just want to make sure we're clear on this. The entries of these cells are how much each food item contains of these 3 nutrients. And then the upper row there is the price of these items, and then these amounts here are how much nutrients, how much of each nutrient you have to consume. The diet problem says, find me the cheapest diet you can, and you have to have at least these requisite amounts of nutrients. This is a great time to pause and think and have a discussion, because figuring out this model is probably the biggest, one of the biggest milestones or biggest hurdles that you'll encounter in learning about mathematical modeling. So I'm going to say the question again. You're sitting in a grocery store. Okay, you see these 6 items ahead of you. I didn't include any vegetables on that list. I didn't include any vitamins in this table either. So this would be a very irresponsible diet, and you shouldn't use it for dietary advice. But you're sitting in a grocery store. You're trying to save your cost. You're trying to be very cost efficient. So you want to choose the small, you want to buy some bread, you're going to buy some milk, you're going to buy some cheese, you're going to buy some potato, and so on and so forth. And you're going to buy these in amounts so that you want the cheapest diet you could come up with, but that diet has to have at least this much of these nutrients. So the diet, whatever you come up with, whatever the amount of bread is that you buy, the amount of milk, and so on and so forth, you have to have at least 46 grams of protein and 65 grams of fat and 250 grams of carbohydrates. That's the idea. So this is a good time for a discussion, although I'll just work through the problem now. Let's work out this problem here. So first of all, we'd say, is this a minimize or a maximize problem? I've written the answer right here. This is a minimization problem because I said find the cheapest diet that you can come up with. Now, often when you ask people, what are your variables, they say, oh, I think it's the nutrients, like you have a certain amount of nutrients that you're trying to consume. But actually, that isn't under your control. You don't want to have a variable for these nutrients because you can't select that. I can't walk into a grocery store and say, I would like to purchase 25 grams of protein. That is not directly under my control. What is directly under my control is how much of each of these food items I'm going to buy. And therefore, you should have one variable for each one of these food items. So we have in my formulation there x1 through x6 because you have x1 is for bread, x2 is for milk, and so on and so forth. My objective function is the cost of my diet. So if x1 represents the amount of bread that I buy, then how much am I paying to buy bread? Well, it's 2 because that's $2 per unit of bread, whether it's a slice or a loaf or whatever it is. 2 times x1 plus 3.5 times x2 plus 8 times x3 and so on and so forth. So you can see that when I add this up, if x1 through x6 represents how much bread, milk, cheese, potato, fish, and yogurt I buy, that linear function there is the total cost of this diet to me. And that's the thing that I want to minimize. Okay, so that's what that is. Minimize the sum of this stuff. Now my ST subject to, and now I'm going to write my constraints. So I've got this thing here, which has to be greater than or equal to 46. That's my constraint. Where does that come from? Well, 46 is the amount of protein I have to consume. And so not surprisingly, 46 has it appears on this side of the inequality because the amount of protein that I consume, which I claim is this thing there, has to be greater than or equal to 46. I have to consume at least 46. So where does that expression come from? Well, so what are these entries here? I've got 4x1 plus 8x2 plus 7x3 and so on and so forth. That's these numbers here. And where do these come from? Well, I've got 4 grams of protein per piece of bread. So therefore, how much protein am I getting from bread? It's 4 times x1. I get 8 grams of protein from milk. So therefore, how much protein am I getting from milk? It's 8 times x2. And you repeat this sum through everything there, and you say that has to be at least 46. Okay, the same for fat and carbohydrates. That's what these constraints represent. And then finally, not surprisingly, all of these variables have to be non-negative. I put in a constraint that says all of them are greater than or equal to 0. You can't buy negative food, right? That makes no sense. So that's a linear program. That's the diet problem. It's the world's most famous linear program, and it is also a very important one. So that's your first. And if you solve that problem, which you will learn how to solve by hand, a problem of this size, I would use a computer. I'll use something called CVX, which we'll talk a lot about later on. You'd find the optimal solution looks like this, that you should buy nothing. You should buy 11.66 cartons, whatever, jugs of milk, and 6.68 cups of yogurt. So a very dairy-intensive diet. Again, it's a stupid model. I'm not factoring in vitamins, but that is what you get. You could also, if you want, there's a lot of versatility to this model here. So you could notice that all of my inequalities went in this direction. There's no reason they have to be. It's just because that's typically how we define the problem. We say you have to have at least this much protein, at least this much fat, at least this many carbohydrates. A lot of times in a diet, maybe you have an upper limit on the fat or an upper limit on the calories, let's say. You go, well, I don't want my calories to exceed 2,000, right? That would... That's kind of a low limit, but we'll work with that. You'd say, okay, I at least this much protein, at least this much fat, at least this many carbohydrates, but no more than 2,000 calories. No problem at all. You get the exact same formulation you had before, but now you add in this extra constraint here that has an inequality moving in the other direction. And you say the total calories has to be less than or equal to 2,000. And you work this out. The diet is a little more varied. It's still a lot of milk and yogurt, but then you also add some potato to the mix there. A former colleague of mine at the University of Minnesota, Lisa Miller, tried the diet problem on McDonald's menu, and she found that the optimal solution was free because you just gorge yourself on free ketchup and mustard and mayonnaise, which shows, speaks to this earlier point about the putting in enough variables to your model to make it realistic, but not too many that you get sort of ridiculous answers like that. This is source code for how to solve this problem in CVX, which is a tool we're going to use in MATLAB, and we'll learn all about that in discussion, but we'll skip through that for now. Production planning. This is the second most famous linear program in the world, and we'll think of it like this. You operate a bakery, and we'll say you make two kinds of cakes. You make vanilla cakes and chocolate cakes. And I've got the recipe for vanilla cake here. I've got the recipe for chocolate cake here. And I sell vanilla cakes for $3 each and chocolate cakes for $5 each. And in my bakery, we'll say we're going to disregard the problem of going to the store. And I'll say I've got in my kitchen in the back, I've got 41 cups of sugar, 24 cups of butter, 80 eggs, and so on and so forth. I'll take all this information and I'll compress it into this table that you see here. Okay, so vanilla cake, these are the ingredients for that. For a chocolate cake, these are the ingredients for that. This is how much of these ingredients I have at my disposal. We'll assume I can't go over that. Of course, you could go to the grocery store and pick up supplies in the real world, but we'll assume I can't do that. And I make $3 for every vanilla cake that I produce and $5 for every chocolate cake. So we'll assume that demand is not a problem. We'll assume that I have a very successful bakery and that people want to go there and buy my cakes. Your problem as a baker is you'd like to say, well, I would like to know how many chocolate cakes and how many vanilla cakes I should make in order to earn as much money as I can. You might look at this and say, well, I should probably make as many chocolate cakes as I can because that makes more money. But it might be the case that when you do that, you end up with a lot of wasted resources left over in your kitchen. Maybe the chocolate cake uses up ingredients in such a way that you end up with a lot of excess of ingredients lying around, and perhaps there's a better way of making money by making a mixture of chocolate cakes and vanilla cakes. Okay, so we don't know off the bat what the right answer is, and we'd like to figure out what that should be. So what we're going to ask ourselves first, we'll build the linear programming model. There's the answer right up there. Step number one, is this a minimize or a maximize problem? It's a maximize problem because we want to make as much money as we can. What are the variables that are under our control? In fact, there are only two variables available to us. There's the amount of vanilla cakes that we make and the amount of chocolate cakes that we make. That's the only decision that I can make. We're going to disregard for now the fact that you can only make you can really only make whole numbers, right? A third of a cake or something. You don't usually see those for sale in a bakery, but we're going to disregard that for now. So there are actually only two variables that are at our disposal that we have control over: the number of vanilla cakes that we make and the number of chocolate cakes that we make. And so if we let x1 be the number of vanilla cakes and x2 is the chocolate cakes, then the amount of money that we make is 3x1 plus 5x2. $3 for every vanilla cake, $5 for every chocolate cake. So that's my objective function, and that's the top part of my linear program. Maximize 3x1 plus 5x2. That's how much money I make from vanilla and chocolate cakes, respectively. And now I have a subject to constraint, and I have a lot of inequalities that look like this. Now, what do these mean? These constraints just mean that you're not allowed to use more of each ingredient than you actually have. Let's look at this first example here. This says 0.75x1 plus x2 is less than or equal to 41. Where did that come from? You look back at this example here. I have 41 cups of sugar available in my kitchen, and each vanilla cake uses 0.75 cups of sugar, and each chocolate cake takes 1 cup of sugar. So the amount of sugar that I'm using in total is going to be 0.75 x1 plus x2, and that is not allowed to be greater than 41. And that's all that I'm doing with these constraints down here. Each one of these just says you're not allowed to use more of an ingredient than you have available. You could look at this one here and notice that it only involves an x2. There's no x1 in there. That's because this last ingredient here is cocoa powder, which doesn't appear in a vanilla cake. If I go back there, you can see, sure enough, cups of cocoa is 11 cups available, and of course you don't use any of that in a vanilla cake. And then again, you have this non-negativity constraint. You can't use negative ingredients in a cake. My mother used to tell me you can't unscramble an egg. It's the same thing here. I can't take a cake and decompose it into its constituent ingredients or its composite ingredients. So that's your second linear program. It's called the production planning problem. People often talk about this involving factories that are making things with the graphite and steel and things of that sort, but I've always thought the baker example is a little easier to remember. If you solve this problem using CVX, using a computer, again, you're going to be able to solve this by hand. But if you solve it using the computer, as I would do, you would get this answer there. The best outcome is actually to make 25.33 vanilla cakes and 22 chocolate cakes. This is a silly cartoon that I'm going to skip right through.